You were brazenly lied to in every geography class. What we've been taught for years as the history of great scientific discoveries crumbles to dust upon the first scrutiny of administrative documents. We are presented with a romantic image of the astronomer who gazes at the starry sky at night in pursuit of knowledge about the universe. However, if you open the financial reports of the 19th century, you will see a completely different picture. These buildings were not constructed for science. They were built by the military, financed by trading corporations, and managed by people from intelligence. Why did the general staff of the largest empire in the world personally oversee the construction of a telescope? Why did priests in China have the right to stop the trade fleets of great powers? How did it happen that the standard of precision for the entire planet was determined privately by a group of people who never revealed their true intentions? And why were star maps created using the same methods as artillery bombardment plans? They show us domes and telescopes so that we don't notice the main thing. These were not temples of science. They were command centers for capturing reality. The main question is, who really drew the map of the world in which you live today? There is a question that no one asks in history lessons, not because it is uncomfortable, but because the answer is too simple, too obvious, and for that reason, the most destructive. The question is as follows: who decided that reality looks exactly the way you perceive it? Not in a philosophical sense, literally. Who decided where the East begins and where the West ends? Who established which device tells the truth and which lies? Who determined what weather is approaching the port and whether the captain has the right to go out to sea? Who measured the shape of the earth and declared the result final? We tend to think that reality is a given, that it exists independently of who studies it. But in the 19th century, a group of people realized something important. Reality does not exist on its own. Reality is what is measured, calibrated, mapped, and synchronized. Everything else is just noise beyond the system's boundaries, and they got to work. Look at how any system of territorial control is built. First, you need a map to know exactly what you are controlling. Then you need standards of measurement so that data from different parts of this territory can be compared. Next, you need synchronization so that commands, schedules, and financial flows operate under the same rules. Finally, you need knowledge of the invisible forces, weather, magnetism, currents, to prevent nature from destroying what you have constructed. These are 4 levels. In the 19th century, a separate object was created for each level, a separate observatory with a specific task. None duplicated another. Together, they covered everything. They show us domes and telescopes. They tell us about astronomers who spent their entire lives looking at the sky, romantic loners dedicated to science. It's a beautiful story. It sells well in textbooks and tourist brochures. But just do one simple check, and the narrative starts to crack at the seams. Here's the check. Take any major observatory from the 19th century. Don't read what was officially studied there. Look at something else. Who it was administratively subordinate to. Who financed its construction. Who interned there besides the scientists. What data was sent out from it, and to which specific agencies. You will not see dreamer scientists. You will see command centers. Each was responsible for their own area of reality. One captured space. Another focused on the accuracy of instruments. The third monitored the weather. The fourth handled the invisible magnetic forces of the planet. None duplicated their neighbor. None were redundant in this structure. It's not a coincidence. It's architecture. In this episode, we will explore 7 objects, 7 different countries, and 4 continents, 7 official tasks behind which were hidden 7 completely different functions. And in the end, you will see a picture that was never shown to you in geography or history classes. A picture of the system that still governs how you understand the world around you. Let's figure it out, step by step. Let's start with space, with the most fundamental question. Where are you located? Imagine a map of the Russian Empire in the mid-19th century. A vast territory from the Baltic to the Pacific Ocean. More than 20 million square kilometers. How do you govern something like that? How do you conduct military operations, demarcate borders, and tax lands that take 3 months to reach on horseback? The answer is 1. You measure them. Accurately, systematically, without gaps. And for this, you need one fixed point. An anchor from which everything else is measured. And it was precisely for this reason that in the year 1839, a facility officially known as an astronomical observatory was built on the Pulkovo Heights, south of St. Petersburg. Pay close attention to the details that don't make it into tourist brochures. The first director of the Pulkovo Observatory, Vasily Struve, was also the leading military geodesist in the country. Not a lover of astronomy, not an academic in a quiet office. A military geodesist coordinating surveys of the entire territory of the empire. This is the first detail. Officers of the General Staff underwent mandatory internships at Pulkovo. Not voluntary, mandatory. This is the second detail. This means that the military command regarded the ability to work with Pulkovo's data as essential as the ability to read a map or handle a weapon. The third detail is the most important. The Pulkovo meridian was the prime meridian for all geographic maps of the Russian Empire until the 1920s. All of them, without exception. This means the following. Any territory not tied to Pulkovo Heights legally did not exist for the state. It could not be included in a military plan. It could not be demarcated from a neighbor. It could not be taxed. A territory without Pulkovo coordinates was a territory outside the imperial system of governance. Calculate the logic. In the mid-19th century, Russia was actively expanding into Central Asia, Kazakhstan, Uzbekistan, Turkmenistan. Each campaign required precise maps. Each demarcation of the border demanded geodetic reference to a unified coordinate system. Every military plan involved verified distances. And all of this went through one point, through one object on the Pulkovo Heights. It was officially referred to as permanent and improved observations for the success of astronomy. The most obvious objection here is that it's just a coincidence. The military is involved in science everywhere. Fine. Then take a look at the staff's work schedule. At the time of its opening, the observatory had the largest refractor in the world, 15 inches, a unique instrument. Yet, compiling star catalogs accounted for no more than a third of the employees' working hours. What occupied the rest? Geodetic calculations, military topography, officer training, processing data from field surveys. The best telescope in the world spends 2/3 of its time idle while the staff focuses on mapping. This is not an observatory with a military unit. It is a military geodetic office with an observatory as its official facade. And another fact that usually appears at the end of a footnote, but should be in the title. Pulkovo was a personal project of Nicholas I, not of the Academy of Sciences, not of the Ministry of Education. It was personally the monarch's project. Nicholas I built the army, strengthened the borders, expanded the territory, and during this same period, he personally oversaw the construction of the astronomical observatory. Ask yourself, what specifically in astronomy interested the Tsar who was building an empire? The Struve arc. That's the answer. It is a geodetic chain made up of 265 points, stretching from the shores of the Arctic Ocean to the mouth of the Danube, through 10 countries, across several climatic zones. The formal goal is to accurately determine the shape of the Earth. The real goal is to create a unified geodetic framework that allows any point in the space from Norway to Moldova to be tied to a single coordinate system with Pulkovo precision. The grandest infrastructure project of the 19th century, now listed as a UNESCO World Heritage Site, wrapped in the packaging of pure science. Now here is something worth checking. Open any military map of the Russian Empire from the archives, whether it's a campaign plan in Turkestan or a schematic of fortification positions in the Caucasus. In the right corner, you will find the network of the Pulkovo Observatory, coordinates referenced to. This is not astronomy. This is military infrastructure using astronomy as a tool. Look at another fact. In 1879, Pulkovo began transmitting precise time signals via telegraph to St. Petersburg. This means that the entire economic life of the capital, schedules, transactions, the functioning of government institutions, was synchronized through a military geodetic facility, not through city clocks, not through church bells, but through the General Staff Observatory. Time and space under one roof, one agency, one entity. This is what it means to control space through the 0 point. Look at the practical consequences. In the 1860s and 1870s, Russia systematically annexed Central Asia. Tashkent, Samarkand, Bukhara, Khiva. Each operation required precise maps of unfamiliar terrain. How do you create a map of territory where there was not a single Russian geodesist before? You send people with instruments, theodolites, chronometers, angle measuring devices, all calibrated in Pulkovo. Every result recorded in the Turkestan steppe was linked to the same coordinate system that began at the heights of Pulkovo. An officer in Khiva works with the same mathematics as an officer in the Petersburg headquarters. Different places, one language of numbers. That is why the military expansion of the 19th century appeared different from all previous conquests. In the past, armies moved by landmarks, rivers, roads, mountain passes. Now they moved by numbers, by coordinates calculated in the headquarters observatory. And here's a detail that is often overlooked when discussing the Struve arc. The geodetic chain passed through 10 countries: Sweden, Norway, Finland, Russia, Estonia, Latvia, Lithuania, Belarus, Moldova, and Ukraine. Each of these territories contributed its geodetic data to a unified system. Through what mechanism? Through Pulkovo as the central hub. This was the first international agreement on the exchange of scientific data in history. Think about who organized this agreement: a military geodesist, on the orders of a monarch who was building an army. Do you still think that it's all about science for the sake of science? Nikolai I understood this when he personally supervised the construction. Struve understood this as well when he simultaneously led the observatory and military geodesy. The astronomical telescope at the Pulkovo Heights gazed into the sky, and the data from it was sent to the general staff. But Pulkovo is only one part of the equation. Russia measured its territories through its own meridian. The British did the same. However, they had one fundamental peculiarity. They measured foreign land. And by this act of measurement, they declared it their own. In the year 1786, an observatory was established in Madras. Initially private, it later came under the control of the East India Company, the very same company that had its own army, its own fleet, and its own scientific headquarters. In the center of the building stood a granite column, weighing 10 tons. On it were 3 inscriptions, in English, in Tamil, and in Telugu. You will be told, this is simply an instrumental foundation, a 0 point for astronomical observations. Okay, then answer one question. Why is the 0 point for astronomical observations signed in 3 languages? Astronomers do not need translation. However, tax inspectors do need it. Land surveyors, who explain to the local population why their land now belongs to a company, do need it. This 0 point is not for the telescope. It is the 0 point for the entire cadastral registration system of India. The longitude of the Madras Observatory was recognized as the baseline for the Great Trigonometric Survey of the subcontinent. Every point on the map of India, from the shores of Ceylon to the Himalayas, was calculated relative to this pillar. Look at the logic of the colonial economy. The foundation of the tax system in British India is the land tax. To collect the land tax, a cadastre is needed. The cadastre requires precise coordinates for each plot. The coordinates need a base point. The base point is Madras. Without this 10-ton granite column, the East India Company could not control the financial flows of the subcontinent. This is not a metaphor. It is a literal dependence. No Madras, no cadastre. No cadastre, no taxes. No taxes, no colonial economy. But that's not all. There is a detail that transfers history into another dimension. From Madras, the so-called Pandits departed. Indian spies recruited by British intelligence. Disguised as traders and pilgrims, they ventured into Tibet, into Central Asia, into closed states where British officers were barred from entering. They carried tools with them, calibrated in Madras. Every step they took, every azimuth, every measurement was recalculated in relation to that very 10-ton pillar. And it was precisely from here, the Madras Observatory, that the height of Everest was mathematically calculated. Before any British person got within sight of the mountain, they simply did the calculations, using data tied to a granite pillar in India. Director Pogson discovered 8 asteroids here, real discoveries that are cited in scientific catalogs, but 90% of his work consisted of other tasks, providing the port with precise time and conducting magnetic observations for the navigation of metal ships. The asteroids were a scientific facade, a reputational armor that protected the project from too much scrutiny. The more genuine discoveries you have, the fewer questions you have about what you're actually doing. The Great Trigonometric Survey of India lasted 50 years, from the southernmost tip of the subcontinent to the Himalayas. Surveyors moved in chains of triangles. Each subsequent triangle relied on the previous one, like bricks in a wall. Accuracy accumulated and was checked again and again. In conditions of tropical heat, malaria, and challenging terrain, it was a colossal engineering feat. And this entire system, this 50 years of work, relied on a 10-ton column in a commercial corporation building in Madras. Remove that column from the equation, and all the mathematics will crumble. Look at the price of this enterprise, not in money, but in lives. Over 31 European surveyors perished during the survey, not in battles, from malaria, cholera, heat stroke. Local workers were not counted in the official reports. 31 people gave their lives to measure foreign land, not to conquer, not to develop, but to measure. Why was it worth such a price? Because without precise coordinates for each plot, there is no cadastre. Without a cadastre, there is no land tax. In peak years, land tax provided more than half of the revenues for the East India Company. 31 surveyors died for this accounting.
The technical challenge was truly monumental. A chain of triangles stretched 2,400 kilometers, from the southern tip of the subcontinent to the Himalayas. At such a distance, even the tiniest error in the base triangle would result in a massive distortion to the north. That's why the surveyors returned to the baseline, double-checked, corrected, and moved forward again and again. It is precisely this system of long-term rechecks that has made it possible to achieve what seems physically impossible. In 1851, mathematician Radhanath Sikdar completed calculations based on data from several geodetic points and arrived at a number. The height of the mountain, which was then simply called Peak 15, 8,840 meters. None of the surveyors had seen this mountain up close. They viewed it from a distance of 240 kilometers through prisms and lenses. They recorded the angles, and the mathematics, based on the Madras column, provided an exact answer. Today, this mountain is called Everest. Its modern official height is 8,848 meters. The discrepancy with the calculation by Sikkim is 8 meters, over a distance of 240 kilometers. This is what it means to control the 0 point. It is not just a coordinate. It is the foundation of the entire spatial control system. Whoever owns the 0 point owns the coordinate system. Whoever owns the coordinate system determines where the boundary lies, where the house stands, and whose land is whose. It is a power that does not require an army. 10 tons of granite and an inscription in 3 translations are sufficient. Since 1872, the observatory has been connected by telegraph to Fort St. George, a military fortress on the shore. Every day, a signal of precise time, based on astronomical observations, was sent directly to the Naval Command. Astronomy and Military Command, all on the same line. The Madras Observatory closed in 1931 after 145 years of operation. By that time, its task had long been accomplished. The subcontinent had been measured, described, and mapped with sufficient accuracy for any administrative and military needs. The data existed. The original was no longer needed. But what she managed to accomplish has remained. All administrative borders of British India, all routes of military campaigns, all land registry records upon which the colonial economy relied. These were the consequences of geodesy, tied to a 10-ton granite column in Nungambakkam. When India gained independence in 1947, the border between the new states was drawn using the same maps, with the same coordinates. The people who divided Punjab and Bengal in 1947 did so based on measurements made in the 19th century by the East India Company. The 0 point on the Madras meridian has ceased to exist, but its trace remains in every border visible on any modern map of the subcontinent. Now, it's a different kind of power, subtler, almost imperceptible. If you control where the east is, you control the space. But if you control which device is deemed accurate, you control everything that has ever been measured by that device. In Richmond, in the Royal Park, there stands a small building in the Palladian style. Kew, an observatory built for King George III in 1769, officially for the observation of Venus transiting across the face of the Sun. A one-time astronomical event. After the event was over, the building was not demolished. He was reoriented, and that's where the really interesting part begins. Kew became responsible for issuing a document without which the captain had no right to set sail. Not the Admiralty, not Parliament, a specific building in the park. This document was called the Kew Certificate. It was a mark of quality for measuring instruments: chronometers, thermometers, barometers, seismographs. The testing of a chronometer lasted 45 days under harsh conditions: temperature fluctuations, various positions of the mechanism, multiple checks. Failing it meant being left without navigation. Every year, thousands of clinical thermometers pass through Kew for medicine. This means that British doctors across the empire worked with instruments that had been certified in one specific building, in one specific park. Consider this calmly. One organization determines which thermometer shows the correct temperature. One organization decides which clock tells the exact time. This is not a conspiracy in the usual sense of the word. It is a documented monopoly on standards. Now ask the following question. If Britain controls whose instruments are deemed precise, whose data is considered reliable? If your chronometer hasn't passed the Kew certification, then your navigational data is in question. This means your maps are unreliable. This means your fleet and trade depend on the goodwill of a small building in the Royal Park. It's not just product quality. It's technological sovereignty handed into one set of hands. Here is a specific calculation that explains why certification had strategic importance. A chronometer with an error of 4 minutes would result in a 1-degree longitude error. 1 degree at the equator equals 111 kilometers. In the mid-19th century, an error of 100 kilometers while navigating through reefs meant not just a delay in reaching port, but the loss of the vessel. Without a Kew-certified chronometer, the captain worked with data that could not be verified. It could not be compared with other vessels. It could not be presented in the event of a maritime dispute or insurance claim. Kew has turned accuracy into a legal category. The certificate was accepted in court as evidence. Your navigational data is valid if the device passed testing in Richmond. If it didn't pass, your records are simply your personal assumptions. Now the next question. French ships also went to sea. German, American, Dutch. Their instruments ultimately were calibrated according to the standards adopted in Kew, because Britain established the largest maritime database. And if you wanted to compare your observations with the British ones, and you couldn't not want to, as there were more British ships at sea than all the others combined, you had to speak the same language of precision. It wasn't called a monopoly, it was called a standard. The difference is just in the word. Now look at how it worked outside of Britain. French captains went to sea with instruments made in France. German ones had German instruments. But maritime insurance companies, which financed the cargoes, demanded guarantees. A guarantee is a calibration document. Where was this document supposed to come from? Insurance regulations in major ports gradually built themselves around the Q standard. Not because someone imposed it, but because the British fleet, the largest in the world, operated according to these standards. Insurers trusted this data. Thus, all other participants in trade had to speak the same language of precision, just to obtain an insurance policy. This is what a soft monopoly is. No threats, only format incompatibility. Look at the next step. In the year 1900, the National Physical Laboratory was established at Kew, a separate state institution with a single task: to preserve the British standards of measures and weights, the standard meter, the standard kilogram, the standard second. The question of how much a kilogram weighs in Britain was addressed at an institution that grew out of an observatory built for the observation of Venus. One small object for a one-time astronomical event, and it gave rise to an organization that defines physical constants to this day. Look at the specific figures. Every year, hundreds of chronometers passed through the testing stands at Kew for commercial and military vessels. A failed chronometer meant that the ship would not sail with precise navigation. A successful one received a certificate, which the captain presented as a document, like a passport for the sea. In the 1860s, the first automatic system for recording atmospheric electricity in the world started operating here. Copper rods on the dome, connected to Lord Kelvin's recorders, continuously monitored the changes in the electric field of the atmosphere around the clock. What exactly they were searching for is vaguely explained in the official reports. In 1908, something noteworthy happened. The magnetic instruments of Kew had to be transported from Richmond to Scotland. The reason? The electrification of London trams began to disturb the readings. Currents from the tram rails were creating interference. Reflect on this detail. The instruments in Kew were so sensitive that the city's electric tram, several kilometers away, interfered with their operation. This is not measurement out of curiosity. These are tools operating at the limit of physical precision. For what purpose? At first glance, it seems like mere scientific perfectionism. But why, then, is it specifically after the electrification of the transport infrastructure, and not after any other event, that the devices need to be urgently relocated? What exactly were they recording that made tram currents a critical interference? Historians usually say, these were magnetic variation observations. Standard geophysics, nothing special. Fine. But if this is standard geophysics, why does it require such sensitivity that street traffic ruins the results? And why were these observations not allowed to be interrupted even for the sake of convenient positioning? Now, the other side of the Atlantic. A different story, but the same logic. In 1854, an observatory was established in the state of Michigan. It was called the Detroit Observatory, even though it was located in Ann Arbor. Why such a name? Because the funding came from Detroit industrialists, not scientists, not the government, people who earn their living from steel mills and railroads. Rich industrialists are investing money in a telescope. The question is, why? Look at the constructive solution that explains everything. The meridian circle of the observatory was mounted on a separate stone pier, completely isolated from the building's foundation, a special design for damping vibrations. Vibrations from what? From passing trains. This constructive solution speaks directly. The object was created under the conditions of an active railway infrastructure, and for it. The Detroit Observatory established the standard of precise time for the Michigan Central Railroad. In the era before time zones were introduced, this was a literal commodity. Cities and companies in the state purchased time from the observatory. They paid to have their schedules aligned with exact astronomical data. 22 discovered asteroids is a real scientific achievement. No one can take that away. But it has been this that built the reputation of a serious scientific institution, one that can be trusted with regulating train schedules. Science as a reputational shield for commercial infrastructure. Industrialists invested their money not in stars. They invested money to ensure their trains did not collide and arrived on time. The observatory was a logistics management system for Michigan, wrapped in a dome and a telescope. Here, standards for weight and measures for the entire state were also kept. Consider this. One building determined how much a pound weighs in Michigan, how long a minute lasts, how much a ton weighs. All trade transactions, all calculations for goods, all railroad schedules, everything hinged on this point. The first program in the U.S. for training in practical astronomy for the needs of westward expansion. Practical astronomy is not just stargazing. It's navigation, geodesy, scheduling. The people trained here did not go into academia. They went with the Army to the Western Territories and took with them tools calibrated in Ann Arbor. Focus on this phrase, for the needs of expansion to the west. This is the official wording of the observatory's curriculum. Not for the needs of science, not for the needs of education, for the needs of expansion, military and commercial development of territories. Another fact that belongs at the end of the official history of the building, but should be at the beginning. The director of the observatory, Franz Brunau, introduced to the United States what was referred to as German precision in astronomical observations. This was a measurement standard, methodological, not just technical, a unified way to observe, record, and process data, consistent across all locations where his graduates worked. This means that the people who passed through the Detroit Observatory carried with them not only instruments, but also a method, a single standard, a unified language of measurements. Thousands of kilometers to the west, in territories that were not yet on accurate maps. This is not a theory, it's a documented history. The Pacific Railroad Survey, a series of military expeditions from the 1850s, was laying out routes for the Transcontinental Railroad. Each expedition included astronomer-geodesists. Their task was to determine the exact coordinates of key points along the route, the latitude and longitude of every mountain pass, every river crossing, and every junction where the tracks were to be laid. People who went through practical astronomy for the needs of expansion headed precisely there. Their observations were transformed into maps of the Western Territories. Decisions about railroad routes, the placement of military forts, and the borders of new states were made based on these maps. Every stake driven into the ground of Nebraska or Utah relied on astronomical data. The chain from star observation to the stake in the prairie, and in the middle of this chain stood a stone pier on an isolated foundation in Ann Arbor. The telescope as a tool of conquest. This is not a metaphor, it is a job description. Look at one fact that clarifies the entire picture. By 1870, the United States had over 300 different local times. Each city had its own. Each state had its own. The railroads connecting them operated on schedules that were incompatible with each other. A train would arrive at one moment, yet the local clocks showed an entirely different time. Collisions occurred precisely because of this. Who established a unified time for the railroads? A network of observatories. Detroit served for Michigan. Similar hubs were created for other regions. They didn't negotiate with each other at conferences. They simply sold their signals to the railroad companies. Gradually, from these regional systems, the American standard emerged. This is how time is captured, not by decree, through indispensability. So, space is captured through meridians. Accuracy is captured through certification and standards. But there is something that cannot be measured by clocks or rulers. The invisible forces of the planet itself, the magnetic field. And it is precisely for it that, at the same time, a completely different group of people was hunting. In the most unexpected place on the map, Tasmania. The year 1840. A small wooden building on the grounds of the governor's residence in Hobart. Built by the hands of convicts. Official name, Rossbank. Official task, measuring magnetic decline and the intensity of the Earth's field. Around the clock, without days off, every 2.5 minutes. For years. Try to imagine this in detail.
Not once a week, not once a day. Every 150 seconds. A measurement. Day, night, storm, heat. People who took turns at the instruments to ensure the flow of data wasn't interrupted for even an hour. What were they searching for? Magnetic Crusade. This is the official name of the program. Not a metaphor, it's the actual title in the documents. The initiator is Colonel Edward Sabin, who simultaneously headed the Royal Society and military intelligence. The goal? To create a global map of the planet's magnetic anomalies. Why? Here's a specific engineering answer. By the mid-19th century, the hulls of sea vessels were increasingly being constructed from metal. A metal hull creates its own magnetic field. This field distorts the compass readings. A ship that does not take into account the correction for its own magnetic field does not know where it is heading. The navigational trap that metal ships fell into was a real, documented problem. Without the map of magnetic anomalies, the ocean became unpredictable for the new fleet. He who possessed this map held dominion over the sea. Calculate the scale of the task. To create an accurate correction table for the navigation of a metal ship, it is necessary to know the magnetic field at every significant point along the ocean route. The Earth's magnetic field is heterogeneous. It varies from latitude to latitude and from season to season. To describe it reliably, simultaneous measurements are needed in dozens of locations around the world and over several years. Individual short-term expeditions did not provide the necessary picture. Only a permanent network can achieve this. This was the Magnetic Crusade, the first planetary system of continuous monitoring. Greenwich, in London. Toronto, in Canada. Ross Bank, on the edge of Antarctica. Each node measured the same thing, with the same instruments, following the same protocols. Ross Bank is the southern outpost of the system. The tools here were identical to those in Greenwich and Toronto. The same instruments, the same methods, the same time protocols, so that data from all over the world would be comparable.
These are not three independent observatories. This is three nodes of a single measurement network. The scale of this network should be appreciated. In addition to Greenwich, Toronto, and Hobart, similar stations operated in St. Helena, Cape of Good Hope, Mauritius, and Bombay, simultaneously, under a single protocol. This was the first planetary network of continuous physical monitoring in history. Before the advent of radio, before the advent of the telephone. The data were sent by mail and still aggregated into a single database. Sabin coordinated this from London for 20 years. Every few months, the stations received new instructions, agreed-upon questions for simultaneous study. It was a scientific organization with military discipline and military objectives. But global synchronization required something more than identical instruments. It demanded uniform measurement timing. Sabin introduced the so-called term days, specially announced dates when all stations in the network took measurements every 2.5 minutes, continuously, 24 hours straight, simultaneously, at all points, over the same days, at the same moment. London, Toronto, and Hobart recorded their readings. What is the purpose of such synchronization? Here's the engineering answer. The Earth's magnetic field responds to solar activity. When a powerful eruption occurs on the Sun, the Earth's field reacts simultaneously across the entire planet. If you have only one station, you see the needle deflection, but you don't know if it's a local anomaly or a global event. With a network, you know. Because at that same moment, the needles in London and Toronto also deflected similarly. Rosebank was situated as far away as possible from the other nodes. Any signal that appeared simultaneously at all 3 points could only be global. Not local noise, not a device error. It was through this network that Sabin discovered that the cycle of Earth's magnetic disturbances aligns with the 11-year sunspot cycle. For the first time in history, the connection between the Sun and the planet's magnetism was proven by data. The straightforward navigational implication of this discovery is that near the magnetic poles, during periods of solar activity, compasses behave unpredictably. Now, this could be anticipated. Knowing the solar cycle meant that you could plan Arctic expeditions for safe years rather than sending a fleet into the unknown, as Franklin did. The construction of Rosebank was carried out under the personal supervision of John Franklin, the governor of Tasmania and one of the most experienced polar explorers of his time. A man who personally participated in the expedition that discovered the North Magnetic Pole in 1831. The observatory was founded by the ships of that very expedition, the Erebus and the Terror. The same ships that went to the Arctic with Franklin several years later and did not return. What exactly did Franklin know about magnetic fields that made him an indispensable commander in polar waters? What map, a real one, not an official one, did he take with him when he went on that final expedition? What specific data is required to navigate the Northwest Passage? And could it be obtained solely from the Rosebank database? We do not know. The ships were found only after 170 years. The documentation is not complete, but the question remains open. There is one more detail worth knowing.
When the wreckage of the Erebus was discovered on the Arctic seabed in 2014, it turned out that the vessel lay in a location that did not match any of the official routes marked on the maps. Franklin was going where the maps did not show. He was following something else. Based on what data? It is unknown. Magnetic maps? Information that existed but did not make it into the official reports. Rossbank collected data on the magnetic field of the South Pole. Franklin was heading toward the North Pole. Both poles are magnetic anomalies. Both required the same type of knowledge. The connection between Rossbank and Franklin's last expedition is unproven, but it is certainly not a coincidence. The Rossbank Observatory was closed in 1854, exactly when the database had been accumulated to a sufficient extent, neither earlier nor later. 14 years of continuous measurements, and that was it. The object had fulfilled its purpose. The task was completed. The staff was dismissed. The building was left empty. But while the British were hunting for magnetism in the southern seas, on the other side of the planet, another group was creating a network of a completely different scale. Not to study nature, but to control information about it. Shanghai, 1872. French Jesuits establish the Zikaway Observatory. Stop for a moment. The Jesuits. A religious order known for its influence in politics, intelligence, and education. They are building a meteorological observatory in a trading port. Why? Here's what they created over several decades. A network of more than 50 observation stations, from Siberia to the Philippines. Every day, they received over 200 telegrams with weather summaries. 200. Every day. This meant that no other organization in the region, neither the British, nor the French, nor the Japanese administration, had the same picture of the state of the atmosphere. It was a monopoly on predicting typhoons. A typhoon 12 hours before arrival means real money. Those who know about the storm sooner than others can delay the departure of a vessel and save cargo worth hundreds of thousands. Or they can choose not to delay and allow a competitor to sink everything. To insure or not to insure. To buy or to sell a future contract on tea arriving tomorrow. Weather has become a financial instrument. Zikaway was officially associated with the Maritime Department of the Chinese Customs, which was overseen by the Briton Robert Hart. The observatory issued permits for ship departures through a system of storm signals. The Jesuits of Zikaway were the only ones whose forecasts were officially recognized by all foreign powers at the same time: the British, the French, the Americans, the Japanese. Everyone looked to the same point, the red brick building with the tower in the Jesuit quarter of Shanghai. It's worth explaining how it worked technically. Every morning, telegrams arrived from the stations in the network. Pressure, temperature, wind direction, speed. The meteorologists in Zikaway processed this data and created a forecasting map, the first in the region. It showed where a cyclone was forming, how fast it was moving, and in which direction. 12 to 18 hours before the storm's arrival, a warning was sent to the port. The port raised storm signals. The captains knew. The Jesuits are warning. It means they should delay or seek shelter. Those who knew about the storm in advance could control the movement of goods. This means controlling prices. This means controlling insurance rates. This means determining who will go bankrupt and who will get rich after each major typhoon. And here is the same detail as in Q. The magnetic department of Zikave had to be moved from the center of Shanghai. The tram lines were causing interference. The same tram currents, the same sensitive instruments, the same necessity to relocate to the outskirts of the city. Q in London and Zikave in Shanghai. Entities at opposite ends of the planet, with different owners and different tasks, have encountered the same physical problem. This is not a coincidence. It is a sign of a unified technological standard. What exactly did they measure besides the weather? Those very terrestrial currents that Q was recording with copper rods on the dome. Atmospheric electricity. Changes in the magnetic field. Those invisible forces to which official history appends the word meteorology and closes the matter. They could not control the typhoons, but knowing about them before anyone else, that they could do. And that knowledge was worth more than gold. Look at how the system operated technically. On the Bund waterfront in Shanghai, there was a signal mast. Combinations of balls and cones were raised on it. A specific configuration for each type of storm. The ball signified one thing. The cone signified another. The number and arrangement of the shapes indicated a third. Every captain, regardless of nationality, knew this code. It was the first unified storm warning system in Asia. Before Zikave, the captain would look at the sky and make decisions on his own. Or he would ask the local fishermen. Or he would wait and hope. After Zikave, one glance at the Bund, and you knew everything the Jesuits knew about the next 12 hours. It sounds like a service. In reality, it was control over the harbor. If the Jesuits raised the storm signal, no ship could formally set sail. This rule was acknowledged by all foreign consulates. The religious order, lacking an army and navy, had the legal right to halt the movement of ships flying British, French, American, and Japanese flags, all at once. Think about it. 4 competing empires, in disagreement on every issue, all followed the signal of the Jesuits. Because information about the weather is more important than national ambitions. And the Jesuits understood this better than anyone else. In 1874, a powerful typhoon approached Shanghai. The Zikave warned in advance. Those who heeded the warning delayed their vessels and saved their cargo. Those who did not lost everything. After this event, the authority of the Jesuits in weather matters became absolute in the region. One typhoon, and there are no more doubts about whose data is correct. Now, consider what this meant in business terms. Shanghai, at the end of the 19th century, was one of the largest trading ports in Asia. It was a hub for tea, opium, silk, cotton, and metals. The daily cargo turnover was in the millions. Whoever knew about a typhoon 12 hours in advance could delay ships in Shanghai and not delay ships in Hong Kong. This meant that the cargo would arrive in Hong Kong instead of Shanghai. Consequently, prices in Hong Kong would drop while they would rise in Shanghai. This is not a hypothesis. This is the mechanics of trade well understood by insurers and brokers of that time. The Jesuits did not trade themselves, but they knew who was trading, and they knew the weather. The combination of these two pieces of knowledge was worth no less than any cargo in the Shanghai port. Zikave operated until the 1950s, when it was handed over to the Chinese Academy of Sciences. Today,
it houses a meteorological museum. The red brick building with a tower stands in the center of Shanghai, surrounded by skyscrapers. Tourists photograph it as an example of colonial architecture. No one explains that it was here that the decision was made every day regarding whether the ship would leave the port or not. Every day of its operation. The last node of this system stands on a hill overlooking Sydney Harbor, and in it, everything together: time, space, signals, control. Before the observatory was built here, there was a fort on Flagstaff Hill. The cannons faced the sea. Soldiers watched the horizon. Then the fort was removed. The cannons were replaced by a telescope. The soldier was replaced by an astronomer. But the hill remains the same. The commanding height over the harbor is commanding regardless of what stands on it. The Sydney Observatory, opened in 1858, was built on the foundation of a prison mill. This fact is usually presented as an architectural detail, but it is a matter of managerial logic. Where the state once kept people in fear, it now held them in time. Exactly at 13 hours, a ball dropped from the observatory tower. Simultaneously, at Fort Denison, a cannon fired. The ship captains in the harbor synchronized their timepieces. The crews on shore heard the shot. The townspeople adjusted their clocks. It was a synchronization system copied from Edinburgh, identical in every way. The same sphere, the same shot, the same time. One handwriting on another continent, in another hemisphere, in another colony. The first government astronomer, William Scott, simultaneously managed a network of 11 meteorological stations across New South Wales. One person, an observatory, plus a weather network, plus cartography. This is not multitasking for a passionate scholar. It's a job description. Sydney was the first point in Australia connected to the electric telegraph. This means that information coming from 11 weather stations was sent in real time to Sydney, and from there on. Where to? To whom? For what decisions? At the observatory, women worked as computers. This is how they were officially referred to in documents. They processed data from photographic images of the sky for an international star catalog. The project involved observatories on several continents. The women in Sydney processed their portion of the sky. Similar groups operated in Paris, Cape Town, and Greenwich. It was a distributed computing network. Before the advent of computers, each node processed its own sector. The center aggregated the results. Here is a specific project that illustrates the scale. In 1887, an international conference of astronomers took place in Paris. The decision? To create a photographic catalog of the entire sky. 20 observatories from 10 countries. Each has its own sector of the sky. Each is required to photograph it, measure the positions of the stars, and transmit the data. Sydney was assigned the sector, from 64 to 90 degrees of southern declination. The South Celestial Pole. That part of the sky that no observatory in the northern hemisphere has ever seen. The women computers of Sydney processed glass plates under a microscope. Each plate represented several square degrees of sky filled with thousands of starry points. Each point had to be measured, recorded, and verified. Hundreds of thousands of measurements, by hand, for years. Sydney's final contribution: data on 10 million stars in the southern sky. Data that later formed the basis for navigation tables for routes in the southern hemisphere. The yellow sandstone mansion on the hill above the harbor was a node of the global information network. It was not a local scientific facility. It was a node of planetary architecture. Stay with the image of women as computers. This word, computer, in the 19th century referred to a person who performed calculations, a living calculating tool. Women were hired because they worked more accurately, attentively, and for less pay. They processed hundreds of glass plates depicting the sky, each under the microscope, each dot by hand. Consider the scale: 10 million star points. Each one is a distinct dimension. For each, you must record the angular coordinates, check against the neighboring plate, and enter it into a table. This is a task that today a computer accomplishes in seconds. In the 1880s, these were years of life for specific women in a specific building on Flagstaff Hill in Sydney. And all this work was not because someone loved the stars. It was because without accurate positions of the southern stars, it was impossible to create navigation tables for ships sailing across the Southern Ocean. Without these tables, errors in longitude are inevitable. Errors in longitude in the southern seas, without lighthouses and coastal landmarks, mean disaster. 10 million points measured manually. That was the cost of accurate navigation in the southern hemisphere. And one more detail about Sydney that is worth adding at the end. When the observatory opened in 1858, each Australian colony operated on its own local time. Sydney had its own. Melbourne had its own. Adelaide had its own. There was no synchronization. With the laying of the underwater telegraph cable from London, this changed. The signal of exact time arrived from Greenwich to Flagstaff Hill. From there, it began to spread across the continent via land telegraph lines. The unified time for Australia began here, on the hill where a military fort once stood. There, where they once synchronized using a cannonball, now they synchronize with an electrical impulse. The essence is the same. Only the speed is different. Who coordinated this network? Where was this center located? What decisions were made based on the consolidated catalog? Official response: it was a scientific project aimed at studying the starry sky. Wonderful. But note, this scientific project required the creation of a global infrastructure with nodes on 6 continents, connecting them to the telegraph network, and organizing synchronized data processing over decades. This is not amateur astronomy. This is industrial scale. There is one more detail about Sydney that is often mentioned at the end of all official descriptions. The observatory was built by the architects of the Colonial Office, individuals who constructed prisons, barracks, and administrative buildings. Not by private scholars or academic institutions, but by a government construction agency, commissioned by the state, with state objectives. This is important. When the state constructs a scientific facility with its own hands, it is not philanthropy. It is infrastructure for governance. Flagstaff Hill got its name from the flagpole of the signal station that stood here even before the fort. Initially, it was a flag used for communication with ships in the bay. Then came the fort, which protected the bay with weaponry. Finally, there was the observatory, which governed the bay with time. 3 functions, 1 elevation, 1 logic of power over the space below. 7 objects, 7 different countries, 7 different tasks, different languages, different owners, different official goals. Pulkovo, the space of Russia. Madras, the space of India.
Q. The precision of instruments throughout the empire. Detroit. The time and measure of the state of Michigan. Rossbank. The magnetic field of the southern hemisphere. Zikave. The weather and information flows of East Asia. Sydney. The synchronization of the colony and data transmission into the global network. None of these functions intersect with each other. None duplicate the adjacent ones. Each is a separate parameter of reality. Together, they form a complete system. The most obvious counterargument is that this is simply the advancement of science. Different scientists in various countries independently addressed the practical problems of their time. Navigation, cartography, meteorology, these were all necessities for everyone. There is no unified plan. Sure, then please answer a few questions. Why were identical instruments used according to identical protocols everywhere, from London to Hobart, when measuring magnetism? These are not just similar devices, they are the same models, the same instructions, the same time intervals for measurements. Who standardized this? Why did the observatories in London and Shanghai face the same problem, tram currents disrupting magnetic instruments, and resolve it in the same way? Did they share a common engineering standard? Where did it come from? Why was the first director of Pulkovo a military geodesist rather than a civilian astronomer? Was it a coincidence or a job description? Why did the Jesuits in Shanghai, a religious order with no ties to the naval authorities, work in official collaboration with the British Customs, which managed the maritime gateways of China? Why was Rossbank built specifically on the territory of the governor's residence? Why did convicts construct a scientific facility instead of the governor commissioning the building from a civilian contractor? Why was the Detroit Observatory officially named after the industrial city, even though it was physically located in the university town of Ann Arbor? What was more important, science or the money that gave it its name? Each individual question has an explanation, but when you ask them all together, the explanations stop working. Too many coincidences, too precise a distribution of functions, too synchronous an emergence. Look at what happens when you consider all objects as elements of one system rather than as separate stories. Pulkovo and Madras sees space, but from different ends. Pulkovo defines its own territory, making it manageable. Madras captures someone else's, making it taxable. Two different methods, one outcome, space under control. Q and Detroit capture accuracy, but from different positions. Q sets the standard through certification. We determine whose instrument is correct. Detroit sets the standard through education. We teach people who carry our measurement method into new territories. A monopoly on the instrument and a monopoly on the method. Together, this constitutes a monopoly on measurable reality. Rossbank and Zikave capture the invisible, but in different ways. Rossbank describes the magnetic forces of the planet, making them predictable for navigation. Zikave describes the atmospheric forces, making them predictable for trade. Two different kinds of the invisible, one function, an advantage over those who do not know. Sydney integrates all of this at the colonial point: time, meteorology, cartography, connection to the global network, and broadcasts a single standard across an entire continent. This is not a random distribution of functions among independent objects. This is an architecture for a system that manages reality, without duplication, without gaps.
There is an exact formulation of what these objects were. It should be spoken slowly, as it changes the way you look at the world around you. In the 19th century, reality was what was measured. Everything else was beyond the system. The land without Pulkovo coordinates did not exist for the Russian state. A ship without a Q-certified chronometer had no right to set sail. A port without a Zikave weather forecast operated in the dark. A territory without a Madras reference was not subject to taxation. They didn't just study reality, they were shaping its boundaries. Look at how it appeared to those who were outside the system. If your land is unmeasured, it is legally unclaimed. Therefore, it can be taken. If your ship is not synchronized, it is unreliable. Its data is not accepted. Therefore, you are not a participant in maritime trade. If your instruments are not certified, your scientific data is not recognized by the international community. Therefore, you are not on the map of knowledge. Measurements are not just a science. They are an act of including or excluding from the system. Those who governed the system of measurements determined who exists and who does not. And here is what is important to understand in the end. These systems did not disappear. They have evolved. Pulkovo served as the prime meridian for all Soviet maps until the 20s of the last century. Its data were used in military operations. The Q grew into the National Physical Laboratory, which still preserves British standards. The United States Naval Observatory in Washington, a direct descendant of that system, now manages atomic time standards for GPS. The very system you use to plot routes on your phone, the International Catalogue of Stars, to which Sydney's data contributed, formed the basis for modern navigation databases for satellites. You use measurements made in the 19th century every day. Every time you open a map, every time the clock in your smartphone syncs, every time a ship departs from port on schedule. You are using a system that someone has built very carefully. You just have never been told the names of the builders, and you were never explained whose interests this system served primarily. I'll tell you one more thing. In 1884, an international conference was held in Washington. Representatives from 25 countries voted for the adoption of a single prime meridian, the Greenwich meridian. 22 votes in favor, 2 abstained. Brazil and France. Santo Domingo voted against. Stop and look at this picture. 25 states, 25 sovereign governments. They gathered and voted to transfer control of the 0 point of the world coordinate system to the military department of one particular country. Voluntarily. Why? Not because they were forced, because by that time the telegraph network, marine trade systems, and international navigation were already operating on the Greenwich Standard. To refuse meant to exit the system. To exit the system meant losing access to marine trade, to navigational data, to credit flows tied to shipping schedules. There was no choice. The system was established before the voting took place. The voting merely recorded what had already happened. Look at how it looked for the countries that found themselves outside the system. Ethiopia, China, Persia. They were not represented in Washington in 1884. They were not invited. Yet their ports traded with British, French, and Dutch ships. Their trade followed a schedule tied to British chronometers, calibrated in Q, synchronized with the Greenwich time signal. They utilized the system without signing a single document, simply because there was no other system. Invisible occupation, without a single shot. This is the highest class of capture, not by force, through indispensability. First, you create the infrastructure without which existence in the modern world is impossible. Then you offer everyone the chance to use it. After that, you hold a vote and receive unanimous agreement. The reality you live in was someone's project. Do you want a specific example of how this works today? Open any navigation app. GPS determines your location with precision down to the meter. How? Satellites. Satellites sync with atomic time standards. The atomic time standards are maintained by the U.S. Naval Observatory in Washington, a direct institutional successor to the system whose first nodes we discussed today. The data on the shape of the Earth used for calculating coordinates relies on geodetic measurements made in the 19th century by networks like the Struve arc. A direct descendant of Madras mathematics formed the basis for the algorithms used to determine mountain elevations. You are not using a new system. You are using the same one. It's just become digital. And this project did not start with declarations and conferences. It began with wooden buildings on the hills above the ports, with granite pillars in tropical cities, with convicts measuring the magnetic field in Tasmania every 2.5 minutes, with Jesuits receiving 200 telegrams a day in Shanghai. It was a project of seizing reality through precision. And it was completed long before anyone realized it had even begun. Subscribe to the channel. New investigations are ahead. Every time you think the story is explained, it turns out that only its visible part has been clarified.